We feel perfectly still right now, but we are sitting on a rock spinning at 1,000 miles an hour, hurtling through a star field. Look at this diagram showing people at different points on the globe. For the person at the top, up points away from the center, but for the person at the bottom, it points the exact opposite direction. Orientation is defined by where you stand. This diagram reveals another perspective trap. To the people standing on the sidewalk, that tree is stationary, but to the passengers inside the moving car, that same tree is traveling backwards. Motion is not an independent fact. It is a combined property of the object you're watching and your own specific point of view. This makes raw human observation an unreliable narrator. Two different people can measure the exact same moving object, record contradicting speeds or directions, and both be correct within their own frame of reference. If you are trying to land a rover on Mars or coordinate a rail network, you cannot rely on subjective descriptions. It creates mathematical chaos. To accurately map reality, we have to strip away our personal perspective. We need a standardized language that treats motion as an absolute, measurable quantity. The first tool is the scalar. A scalar measures pure magnitude, or raw size, tracking how much exists without defining direction. Vectors provide a more sophisticated measurement. A vector binds that magnitude to a precise path, defining both its size and exact orientation in space. Anchoring magnitude to direction allows us to plot every movement on a standardized coordinate system, bypassing the inconsistency of individual perspective. This diagram shows distance, a scalar quantity tracing the total, erratic path an object takes from point A to point B. Displacement is the vector version, ignoring the actual route to focus only on the straight-line trajectory from the start to the final position. By filtering out the inefficiency of the path, displacement reveals the net change in an object's physical location. This same logic applies to time. Average speed is a scalar. It calculates total distance covered over a time interval, regardless of the direction. Average velocity is a vector. It links straight-line displacement to the plop, requiring a specific direction for the measurement to be complete. Because velocity is direction-dependent, it can change even if speed remains perfectly constant. Turning a corner at a steady 50 miles an hour alters your velocity vector. We distinguish broad averages from a single moment. Look at this distance versus time graph. The steepness of the tangent line touching the curve indicates instantaneous speed, exactly how fast an object was moving at one fraction of a second. Velocity provides the complete record, tracking the precise, directional progression of an object through space and time. When an object maintains a perfectly constant velocity, with no change in speed or direction, it is in uniform motion. This straight diagonal line shows distance increasing at a perfectly steady, predictable rate. When velocity fluctuates, we use a new vector to measure that shift: acceleration. Acceleration is the rate at which an object's velocity changes over time. This applies to any change in the vector. Slowing down by applying the brakes is a form of acceleration, as the object's velocity is actively decreasing. This leads to a surprising result. Look at this object moving in a circle. Even if its speed is constant, it is accelerating, because these tangential arrows are constantly shifting their angles to follow the curve. Acceleration accounts for every alteration to a moving object's state, providing the data needed to calculate where that object will be in the future. These variables, initial velocity, final velocity, time, displacement, and constant acceleration, link together in three fundamental equations of motion. These formulas act as a predictive model. If you know a few starting variables, like the initial speed of a car and its rate of deceleration, you can calculate exactly how many meters it will travel before coming to a stop. These equations transition kinematics from a method of observation to a system of prediction, providing the exact coordinates of an object seconds before it arrives. This mathematical precision allows us to calculate the exact burn time and trajectory needed to place a satellite into a stable orbit around the Earth. We began with conflicting human perceptions that couldn't agree on direction or speed. By developing a system of vectors and acceleration, we created a language that lets us interact with the physical world through absolute, measurable data.